So last time we started study of quadratic extensions of Q. We computed ring of integers of a quadratic number field, and then we computed the splitting behavior of primes. So let me do one more example of splitting behavior in a particular number field, and then we will look at relationship between what are called binary quadratic forms and class groups of quadratic number fields, at least for imaginary quadratic fields. Okay. So here is one more example. So if I take k to be q square root of minus 1, right, the Gaussian integer, so this is also often written as qi. Then what is the discriminant? Minus 1 is 3 mod 4, so this is 4 minus 4, right. And so P is ramified if P is equal to 2, and P is split if minus 1 over P is equal to 1, which is if and only if P is congruent to 1 mod 4, and this is inert if 1 over P is minus 1 over P is minus 1. This is if and only if P is congruent to 3 mod 4. Let me take this a little bit further, and as an application of this, we will prove that a prime P can be written as a sum of 2 squares, an odd prime P can be written as a sum of 2 squares. So let me write that down as a proposition. This I think is originally due to Fermat. An odd prime P is a sum of 2 squares if and only if P is congruent to 1 mod 4. Okay, and how do we do that? Well, let us say that P is congruent to 1 mod 4, then P times OK is P1 P2 for P1 not equal to P2 primes in OK. But we also know, or if we do not know yet, we will prove this, that K, this is Qi, has class number 1. Okay. The Minkowski bound of this is really small, so I think it is less than 3. So you only need to check what happens to 2, and 2 is ramified anyway. So 2 is 1 plus I square. Okay, the prime ideal generated by 1 plus I and its square. So that is how you show that the class number is 1, but we will do the class number computations later on. Okay, so do not worry about this. Okay, so P1 is A plus IB for some A plus IB in OK. Now we look at norm of P1. So norm of P on the one hand is P, and on the other hand it is A square plus B square. Okay, so hence P is A square plus B square is the sum of 2 squares. Okay. On the other hand, if P is equal to A square plus B square, then P is also A plus IB into A minus IB. Okay. Now there are two possibilities, right? Where, if the ideal generated by A plus IB is same as the ideal generated by A minus IB, then P ramifies, and hence P is equal to 2. But P is an odd prime. Hence, therefore, these two ideals A plus IB is not equal to A minus IB. Okay. Hence, P splits. Hence, P is congruent to 1 mod 4. Okay. I mean, for this converse, you could just say that if P is 3 mod 4, then A square plus B square is 2 mod 4 or 1, 2 or 0 mod 4, and that is why you can't write it this way. But anyway, we are using more algebraic number theory than is necessary in this part. So you see an application of what we have proven now to the sum of two squares problem. Okay. All right. Now moving on, let me tell you what a binary quadratic form is. Okay. So a binary quadratic form is an expression of the form is a homogeneous degree 2 polynomial in two variables. Okay, so i.e. it is of the form A x squared plus B xy plus C y squared. Okay, because it is a homogeneous polynomial of degree 2, these are all the terms that can occur in it. Okay. Its discriminant is defined as b square minus 4ac, and you shouldn't be surprised to see this quantity. This is exactly the kind of expression that appears if you are trying to solve quadratic equations. Okay. All right. So one aim would be find, so given A, B and C, A, B, C, find all integers that can be written as ax squared plus bxy plus cy squared equals 0, that can be written as this. So, right, for some x and y in z. Okay. So, for example, if you take 1, 0 and 1, we found all primes or odd primes P such that P is x squared plus y squared. And with a little bit of work, you can find all integers that can be written as x squared plus y squared. Right? You may have even seen this in some elementary number theory course, that you can write an integer n as x squared plus y squared if and only if n is either 0 or n is positive and the prime factors of n that are congruent to 3 mod 4 appear to even powers. Right? That's the complete answer to this question. So in this case we have a very satisfactory answer, and we would like to know what happens in general. Okay. By the way, in this case discriminant is 0 square minus 4 times 1 times 1, which is minus 4. And it is no coincidence that we were using to solve this problem, we used a number field of discriminant minus 4, namely Qi. Right, okay. So before we go on to relate this to quadratic fields, let me say that if you, another way to write quadratic forms is the following. So another way to write binary quadratic forms is as follows. You take x, y, you take a, b by 2, b by 2, c, and then x, y. And so if you look at this matrix multiplication, this is ax plus b by 2, y, and b by 2, x plus cy, xy, which is ax square plus b by 2 xy plus b by 2 xy plus cy squared, which is ax squared plus bxy plus cy squared. Okay. So you can think of these symmetric symmetric 2 by 2 matrices with coefficients in half of z, at least the non-diagonal coefficients in half of z, as binary quadratic forms also. Okay. So if you, the advantage of looking at it this way is the following. So let SL2 SL2Z be set of all A, B, C, D in M2 of Z such that determinant of A, B, C, D, which is AD minus BC, is equal to 1. Okay, so determinant is exactly 1. Right. Okay, fine. So, so you can replace, okay, so let P, Q, R, S be in SL2Z and A, B by 2, C, B by 2, C be a binary quadratic form as before, right. So, yeah, okay. So I can consider P, Q, R, S, A, B by 2, B by 2, C, and then P, Q, R, S transpose, right. So what is this? This is P, Q, R, S, A, B by 2, B by 2, C, and then P, R, Q, S. And if I try to write this out, yeah, maybe before that I should say, if you look at determinant of A, B by 2, B by 2, C, this is AC minus B square by 4, which is minus 4 times B square minus 4 AC, which is minus 4 times the discriminant. Okay, so determinant of the matrix has a very simple relationship with the discriminant. Okay. All right. So, if I write this out, it will again be some, it will look like a complicated mess, but it will again be a symmetric thing with half integer entries of diagonal, with possibly half integer entries of diagonal, right. Nobody said that b could not be even, so then b by 2 would be an integer. Okay, but let me write it out for your benefit. So this is p a plus q b by 2, p b by 2 plus q c r a plus s b by 2 r b by 2 plus s c, and then p r q s. So this thing you can write as p square a plus p q b by 2. Yeah, it's kind of, yeah, I mean there is a better way of, yeah, anyway let me write it down and I will tell you a better way of thinking about this soon enough. So plus p q b by 2 plus q square c, right, and then you keep on going like this. So this is p r a plus q r b by 2 plus p s b by 2 plus q s c, and then the same expression will appear here. That's the point, right. So p r a plus yeah, this times yeah, p this times so p s b by 2 plus q s b by 2 plus okay, so what did I do? P r a p s b by 2 r q b by 2. So this should be q r b by 2 and then q s c. Yeah, so that's fine. And then p square a plus no, sorry, not p square a. What am I saying? This should be r square a plus r s b plus s square c, right. I mean the reason why this the diagonal terms look like value at the binary quadratic form is because you are indeed multiplying the matrix by PQ and RS and RS. So the off diagonal terms look a little bit more complicated, but the diagonal terms are precisely values at the binary quadratic form. Okay. Furthermore, we know that determinant of P, Q, R, S, A, B by 2, B by 2, C, P, Q, R, S transpose, this is equal to product of the individual determinants P, Q, R, S, determinant of A, B by 2, B by 2, C, determinant of A, P, Q, R, S transpose, but the first and the last determinant is 1. So this is AC minus B square by 4 times 1, right. So this is determinant of A, B by 2, B by 2 and C. So that's one thing, okay. The second thing is, if n is equal to a x squared plus b xy plus c y squared, let me give this thing a name. So, let me call this a prime, b prime by 2, b prime by 2 and c prime. Then n is also equal to a prime x square plus b prime xy plus c prime y square for possibly different x and y. Okay, what is the x and y that you get? So, another way of writing a is x, y, a, b by 2, b by 2 and c and x, y. Right. But what I can do is I can take x prime y prime such that x y is equal to x prime y prime p q r s, right. I mean, you just take x prime y prime to be x y p q r s inverse. So, this is still in z, this is still in z too, and similarly, so you get so you get n is x prime y prime p q r s a b by 2 c p q r s transpose and x prime y prime, because transpose of x prime, transpose of the row matrix is a column matrix. Okay. Okay. So, so here is a definition. We say that two binary quadratic forms are equivalent . So, two binary quadratic forms, maybe I should give them a name, ax square plus bxy plus cy square and a prime x square plus b prime xy plus c prime y square are equivalent if there exist p, q, r, s in SL2 of z such that a prime, b prime by 2, b prime by 2, c prime is p, q, r, s, a, b by 2, b by 2, c, p, q, r, s transpose. Okay. So, what have we proven? We took all, so okay, before saying what we have proven, let me say the following. So, let S be the set of all binary quadratic forms okay. Then SL2Z acts on S, right. You take a binary quadratic form and you get another binary quadratic form by this action, and we call these two, the orbits of this are the equivalence classes. Okay. So, that is why it is clear that it is an equivalence relation because you have these equivalence classes come from action of a group. Alright, that is one thing, but if I let SD be the set of binary quadratic forms, the set of all binary quadratic forms of discriminant D, right. So, SD is a subset of S. Now, we have shown that SL2Z also acts on this. Not only does it act on S, it also acts on this SD, because if you take a binary quadratic form and you act by some element of SL2Z, you get a binary quadratic form of the same discriminant. Okay. And what did we prove? We proved that two binary quadratic forms, we proved equivalent binary quadratic forms represent same integers, same set of integers. Okay. Represent means that they can be written as a value of this binary quadratic form. I am not at all saying converse, that if two binary quadratic forms represent same set of integers, then whether or not they are equivalent, that's a converse to this. Okay. I am not saying that, I am just saying that if two binary quadratic forms are equivalent, then they represent the same set of integers. So, it makes sense, hence it makes sense to study equivalence classes of binary quadratic forms of a given discriminant, given fixed discriminant D. Okay. So, what are we studying? We are studying SD modulo the action of SL2Z. Alright. So, this is what we will study next time, at least in a special case when D is less than 0. But before I stop today, let me tell you what the significance of D less than 0 is. Okay. So, let ax squared plus bxy plus cy squared be a binary quadratic form. Okay. So, what I am going to do is I am going to consider az square plus bz plus c equal to 0, and what are the roots of this? So, roots of this are, so let us say that a is bigger than 0. Okay. So, say a is bigger than 0, because if not, I am just going to change the sign of the whole thing of a, b and c. So, I will just assume that a is bigger than 0. So, the roots of this are minus b plus minus square root of b square minus 4ac by 2, right. And so, roots are real if and only if b square minus 4ac is bigger than or equal to 0. So, what happens if the roots are not real? So, what happens? So, there are two cases. So, case 1 is b square minus 4ac is less than, maybe 3 cases, but let us say there are this is the case, b square minus 4ac is less than 0. Okay. and A is bigger than 0, so C is bigger than 0. Okay. Then A square, sorry, not A square, A x square plus bxy plus cy square is always bigger than 0 for x and y not equal to 0 comma 0. Right? Because this is same as asking when az square plus bz plus c is bigger than 0 for a non-zero integer z, or the other way around, a plus bz plus cz square is bigger than 0. And because we have no complex roots, so this thing will always be above the above the 0 line, right. So this is always positive, right. So binary quadratic form, a x square plus bxy plus cy square is called positive definite if discriminant b square minus 4ac is less than 0. Okay. So all right. So you can similar so I think it's a good point to stop today, but you can similarly analyze what happens when b square minus 4ac is bigger than 0, and what happens when b square minus 4ac is 0. In any case, the positive definite quadratic forms are of interest to us. These are the only ones that we are going to study. So I won't say much about the other ones. Okay. Next time we will relate these positive definite binary quadratic forms to ideals in or ideal classes in imaginary quadratic field. Thank you.